Hello Internet, this is Sean McBride, and today I want to talk to you about a project I've been working on this past semester for a course I've been taking at George Washington University. The course was CSCI 6421 Distributed Systems, and the professor was Professor Rusba. The team that I worked with on this project included myself, Alvaro, Tyler, and Naeem, and we had a pretty productive semester. So many of you are probably familiar with the idea of a hash table. The concept is relatively straightforward. A hash table basically maps a particular key to a particular place in memory. And often that place in memory holds a value. Sometimes we have some collision detection techniques, so there might be multiple values in that place in memory, which we call a bucket, that we have to either probe or use some other sort of collision detection techniques to resolve. But the core idea here is we have a key, we have a value, we map a key to a value, and the mapping is created by a hash function. So a hash function could be like a cryptographic type hash. Oftentimes for hash functions, we don't really care about the cryptographic and security properties as much. We just need a way to map keys to values. And the values here constitute essentially the namespace of the hash table. So all the possible values that the hash function comes up with. The idea of a distributed hash table extends a hash table, and it's pretty much identical. The only new idea is that realizing that we can perhaps take that namespace that the hash function comes up with, and we can distribute that across multiple nodes on a network. And there's all sorts of different ways to do that. One way in particular is Chord. So Chord is a peer-to-peer distributed hash table, and peer-to-peer essentially means that all of these nodes in this logical network are equal. So they all field requests, they communicate with each other as equals. And this algorithm has been pretty influential, and it's led to a lot of follow-on research by other researchers. So essentially there are just a couple of core ideas here. So the distributed part is based on the idea that when we are using our hash function, we can not only put in our keys and produce values, but we can also put in IP addresses or host names and ports, and basically use that to place, to map a network location to a place on the logical overlay network of our distributed hash table. And so then based on the location of these nodes in the namespace, we can then partition and assign pieces of our distributed key value store out to these different nodes. And so you can kind of imagine each of these circles here are nodes in the Chord network, and the overlay network forms a logical ring, and the logical ring is formed by each node knowing about the next node and the previous node. And you can imagine that since these are different nodes and they might be located all over the world, since this is a peer-to-peer network, it can be really disadvantageous from a performance perspective to have to just kind of crawl along the outside of the ring, right? So if we make a request and we go to this node and we have some data that's stored on this node, if we just were to kind of walk the outside perimeter, we'd go next, 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 right? And each of these would be a network request to potentially a node that's located anywhere in the world. Could be pretty slow. So one of the key ideas of Chord is that in addition to this chain, kind of this circular ring of next relationships, we also have something called a finger table. And you can kind of think of this as like it's like a portal that you can kind of hop through to or I don't know, it's a super highway for your logical network. So each node basically keeps track of shortcuts to other nodes, and the relationship for that is essentially 2 to the m minus 1. So the node knows about its immediate neighbor, of course, which is 1. It knows about the following neighbor, 2. And then since it's 2 to the m, right, it doesn't know about the third. It does know about the fourth. And then each time is multiplied by 2. So it knows the fourth, it knows the 8th. If the chord is big enough, it knows about the 16th. But what that means is that at the very best case, the shortcuts only extend out to basically the node that's on the exact opposite end of the chord. And so the entire second half of the overlay network has no shortcuts. So that means you have to do a couple of hops basically to get there. So one of the innovations that my team added was basically replacing the mathematical formula that determines the way that the finger tables are structured, and basically we're using Fibonacci numbers instead of 2 to the m. And the trade-off there is we are able to have shortcuts further into the overlay network, but then we basically have a larger finger table, and there's overhead involved in maintaining that, and a little bit more memory required to store that. In our case, we thought that was acceptable. So here's the system architecture for what we built. Here on the right, this is basically the Chord peer-to-peer system. Instead of showing it as a logical ring, I'm just showing all these kind of nodes collapsed, but as I showed before, really this is a logical ring. All of these components over here are external to the peer-to-peer network. They're essentially clients of it. My team has created all these different components. We have a data visualization component, which presents basically a monitoring UI that shows the overlay, the logical ring of just like this basically, but it's constantly updating. And so you can basically watch the chord grow and shrink as different clients join the overlay network as peers. And so to be able to do that, we have a special crawler, and you can kind of think of it like a web crawler, but in particular just kind of walks the overlay network and then updates a view of the chord network. And then we have a data API, and the data API provides a command line interface for just doing kind of your traditional create, remove, create, retrieve, update, delete operations for the data. And in the case of our application here, we're actually using Stack Overflow data from the computer science community. So actually all Stack Overflow data is open data and available to researchers. So that's what we basically seed our overlay network with, and that turns our Chord into basically a user service. And so what that would then theoretically allow us to do is we could build a single page web application which could query different peers on the Chord. But we haven't actually built this kind of web application part because it doesn't really teach us too much about distributed applications, and we know how to build web apps, so no issues there. If we want to take a little bit more of a look at our overlay network, here you can see here is that logical ring, in this case just showing with 3 different nodes. The nodes are communicating with each other using gRPC, which is a protobuf based RPC framework, and that was released by Google. And it's pretty popular in industry right now for a variety of reasons, one of which is that it has strong support for all sorts of different languages. So we're using Node.js, which is a JavaScript, server-side JavaScript runtime, and it had pretty good gRPC support. So that's what we're using here. And if we zoom into our nodes, you can kind of see some of the different components here. This shows some of the internal software architecture. Basically, we've written things such that we have a Chord node library, which provides some of the base functionality for building a distributed hash table using the Chord algorithm. And then our application-specific logic, in our case, the Stack Overflow user service, extends that. So these are both classes, which is a pattern that isn't super common in JavaScript, but we thought it was a good fit here. So this is the base class, and this is the child class. So then the instance of the user service is accessed all these methods and things. We also have something that's kind of neat here. It's so Node.js is traditionally thought of as a single-threaded runtime, and that's mostly true. I mean, there's some complexity there based on the C++ libuv stuff that it uses, but we're actually using a feature in Node.js that's based on kind of the idea of a web worker in the browser, and that's basically it's you can kind of think of it like a thread. So the user service or our node is basically has a main thread which runs all the kind of application logic and fields requests to insert, remove users, and update and maintain all the Chord metadata. And then we have a separate thread that runs our SHA-1 hashing algorithm, since it's kind of compute intensive and blocks. And we just pass messages back and forth for that. So I'd like to just give a brief demo to kind of show how everything works. I'm going to show the data API and give you a little bit of an idea for that. And then I'm going to just crank up the number of nodes in our cluster to show that we can scale it up pretty good. Okay. All right, so let me just hit refresh here. All right, so we have 2 nodes up right now. I'd like to just mention that these nodes are running on Docker using Docker Compose. And so we have a web component, which is the part that I showed on the architecture diagram, responsible for building out this data visualization component. And then we have the node primary and node secondary. And the only thing that node primary does is it's mapped with a particular host name and port. So node underscore primary 1337. And we just need that because when we have our secondary nodes come up, they need to have a particular network address that they can ping to be able to join the Chord network. That could be accomplished with different ways, like load balancer or all sorts of other networking techniques, but I'm keeping it kind of simple here just for this Docker Compose. But the key idea here is that this is peer-to-peer and all these are the same. So even though this has a particular special name, that doesn't reflect any special application logic. Okay, so we have our 2 nodes up, and if we click on the nodes, we can see some information about the node that's selected. So here's 658, hostname, port, and then we can see the predecessor, the finger tables, and then we can see users. So I already basically ran the data API, and let me just kind of go back to show what that command looked like. There we go. So I've got this bulk insert command, and what this does is it opens a particular JSON file, which is this tinyusers.json. And this is the data that Stack Overflow essentially made available about its users. And you can see it's like actual user data here. And the the data API basically steps through the JSON and then inserts all these different users. And so we can see quite a few different users. So here we have like user 82. And we can see user 82 is stored at two places. The first one is 666. I guess mark of the beast is the first hash that the hash function developed. And that is here on 822. User 82 is also stored at 473. So if I go over here to the other node and look for 473, we can see user 82. And the cool thing about that is that means the user is stored in two different places on the Chord overlay network. So if a particular node were to go down or just crash or whatever, we still have a copy of the data up. There are additional ways we can improve our solution to be able to, periodically check to make sure is the backup of my data up, or do I need to replicate that, which we don't have right now. So currently, if one of the nodes were to go down, we would still have the data, but we wouldn't then recopy it. So obvious improvement in the feature. And I can pretty easily just go ahead and add a new node to the cluster. And what we're going to see is we're going to see users basically migrate over to that new node. Okay, should pop up pretty quick. Okay, there we go. So now we have 3 nodes. And what I would expect here is that our new node here, 353, has basically been reassigned a bunch of users from, where would that be? I guess from 822. Yeah, and so we can see a bunch of different users here have migrated. So things are working pretty well. And the cool thing about Docker Compose here is that we can scale this up pretty seriously. Generally, I've found that maintaining the overlay network is kind of problematic when a lot of nodes join at the exact same time. So that can be kind of a problem when I use a tool like Docker Compose. It would be less of a problem in real life because these would be actual physical nodes on the network with different sort of network latency characteristics, and that would basically ensure that nodes wouldn't necessarily join at the exact same time. But for the case of this demo environment, it's a little bit more of a problem. Usually it can recover, but it can take a little bit of time. If I were to really just slam this and have like 50 nodes try to join at the exact same time, that would really be problematic. But yeah, I'll just crank it up a bit. I've been able to scale this up to effectively 50 nodes or so. And at that point, the way that we do communication across our overlay network to maintain the finger tables gets a little bit more problematic. And so if I were to turn this into a production application, I would definitely want to do a lot more distributed tracing to understand exactly what is happening with our gRPC calls and why is kind of the maintenance of our overlay getting expensive, because obviously a lot of peer-to-peer applications scale far beyond 50 nodes, and I think it would be pretty easy to deal with that stuff. It just the main problem is just instrumenting the application to be able to handle that. So just adding a bunch here. I mean, you can kind of see it seems to be pretty stable. The updates are actually occurring a little bit faster than what you see on here, but we have that crawler that crawls one node to the next, and it just takes a little bit of time to walk this whole overlay network. Okay, so that's our application here. Everything's working pretty good, like I said, up to about 50 nodes. So I want to just show a couple of things here in the source code. So like I mentioned before, we're using Docker to basically deploy our system locally and develop against it. And that's been pretty great. And one of the really cool things about that is the deployment for this onto an actual cloud is fairly simple. So I don't have it running right now, but I created essentially a template to be able to deploy our solution to Azure. We've been deploying to Linux, but since we're using Node.js and gRPC, we work on both Linux and Windows Server if someone were to want to use that for some reason. We've had several members of our team develop on native Windows. I'm using Windows Subsystem for Linux, so more on the Linux side myself. Yeah, and then our application logic here is basically in Chord node and user service. And here's that crypto thread thing, the separate thread that I was talking about. And yeah, it's pretty simple, basically just calling this library, computing the hash, turning it into a string, and returning it as a message. And so if you were, for example, to want to build a new Chord-based application, the process of doing that would be essentially to take a look at what we've done in user service, how we have our class user service extends Chord node, and then we would essentially follow the same patterns here. The main difference is you just have application specific methods on your implementation class, and then you would have some sort of Node.js script like Node.ts here, and that would basically run your logic and do some of the glue code. So you can kind of see some of the grosser glue code down here. So since we have attempted to support both Linux and Windows, this is kind of inevitable that when it comes to things like sending signals, for example, like the SIGINT here, the cross-platform compatibility stuff can be a little messy. And so we have kind of platform-specific code if, Win32 do this, otherwise do Linux stuff. So what are you going to do? But yeah, our implementation is in Node.js. We're using TypeScript, which is nice because we get all the nice kind of type annotations and error messages that many of us are familiar with from more strongly typed languages. And the reason we basically chose Node.js is it kind of seemed like the lowest common denominator programming language for most of us. We had experience with Java, with C#, with Golang, with Rust, and so Node.js with TypeScript in particular just ends up being kind of like a good C family of languages scripting language, which is pretty quick and has a good collection of third-party libraries through NPM. So it's pretty good prototyping language for the kind of work we're doing here. One of the neat things of choosing to use gRPC is that we have all of our RPC calls and message structures encoded in this kind of language agnostic way. So what that means is if in the future we thought, hey, we've come up with a really good API surface area using Node.js, and we were able to do that pretty quickly because we were using more of a higher level scripting language, but we want to make this really performant and scale out, then we could then take our protobuf and we could re-implement our logic using something like Go or Rust or C++ even. And I don't know, maybe that would help with some of the scalability issues I mentioned past about 50 nodes. Yeah, I think that's pretty much everything here. I mean, so here's that chord crawler logic, which is, it's kind of neat. I enjoyed working on this particular part. So advance walks along the outside of the network, and one of the things that was kind of fun from a computer science perspective is you basically having to detect a cycle. Like when you're walking along the outside of the overlay network, when do you get to a node that you've already been to before? And if you have then walked a complete cycle and there's a node that you visited before that you didn't hit on this walk basically around the overlay network, what does that mean? Is that node down? Did the overlay network perhaps lose its structure and kind of become bifurcated into two different overlay networks? And so as we were experiencing all sorts of different problems earlier on, the logic to kind of be able to visualize this was something that we kind of had to work on side by side. And so now the code, or the chord crawler, is able to basically do walks around, and then nodes that it doesn't encounter on a cycle, it then tries to basically contact and walk from starting with those nodes. So that would detect if for some reason an overlay network split into multiple versions. And I guess it would be possible if maybe like a lot of nodes were running on a corporate intranet or something like that, and then the gateway went down. Like I would expect that those nodes on either side of the gateway would then repair the overlay network, but they would then be two different isolated rings at that point after a while. So the chord crawler can detect that, and it can also then prune nodes as they come down. So we kind of showed it going up, but if I want to take nodes down, that should work fine as well. This might take a little bit. There we go. So we saw a node disappear there. So it looks a little bit funky as the chord crawler walks along the outside, but eventually all this gets repaired. Yeah, so that's pretty much everything. We have some notes here to align our project to the course objectives. So architecturally, we've built a peer-to-peer distributed hash table. We've internally structured all of our work to support reuse as a Node.js library. So if you want to build a peer-to-peer application, we have a library for you. Our system is multi-process. By multi-process, I mean we are running multiple independent Node.js runtimes that act as peers in our peer-to-peer network. We sandbox those peers in a container just to simplify deployment. And each of our independent processes uses Node.js multi-threading support to offload the SHA-1 hashing. And that's pretty important because you really don't want to block Node.js since it's asynchronous. So if you were to do compute intensive workloads such as running a hashing algorithm, it can really kind of slow down being able to service external gRPC requests, which is something we wouldn't want. Communication, we're using gRPC and protobuf, and we use that both within the cluster. So all these different nodes are communicating with their next and previous nodes and updating the finger tables all using gRPC. And then our clients and our data client down here and our web application here are all using gRPC. Not sure if I showed it before, but there we go. That's issuing a gRPC request to look up a user here, user ID 82, and we see username JMAD. Again, this is a Stack Overflow user, so these are like real links and stuff. If we want to open that up, so this guy looks like kind of a math nerd. Yeah, so the network, our system needs some sort of orchestration system. We're using Docker Compose here to run locally. If we were to deploy to the cloud, like I showed that Azure configuration script, you kind of have to re-implement certain things for the hosting environment. Naming our nodes and data keys use a consistent configurable namespace. And okay, where is that? Here we go. We have a couple of just configuration settings here. So the bit length here determines the size of the namespace, and then our is_Fibonacci chord flag here determines if we use the custom Fibonacci based finger tables, or we use the 2 to the m based finger tables, which the original paper discussed. So you can flag that and do performance comparisons if you want. This includes the local keys within the nodes. Yep. Okay. Synchronization. Our nodes have particular maintenance functions they run on set intervals, and that's used to update the finger table, because since this is a peer-to-peer system, we're going to constantly have nodes entering and leaving, so we need to be able to just make sure that all of our view of the overlay network is roughly kept up to date. And then of course we can't ultimately know that the finger table is going to be totally perfect, because as this overlay network gets really big, it's just going to be like harder to maintain every single entry. So, and that's fine. I mean, the worst case scenario is you basically have to do a few more hops to get the data you want. So this is just kind of a progressive enhancement, I would say, this finger table. Consistency replication, we showed our data is inserted in 2 different locations in our namespace, and that gives us a bit more ability to handle unplanned node failures. If our nodes gracefully leave the overlay network, they do transfer the users as they're coming down. So it's just really if we were to have a network glitch, or if a node were to crash, that's when you'd potentially have data loss. And by inserting in 2 different locations, we can be a little bit more confident that we're not going to lose data. The lookup by this data API attempts to find the primary value, and then it falls back to the secondary if it's not found. Just for demo purposes, I have broken transparency a little bit here to basically show where the data we're getting is coming from. So this isn't something I'd normally expose, but we can see that this user data came from the primary node, which is 473. And so if we were to, for example, get data back and this were to be isPrimary hash false, we would know that there was some sort of issue accessing that user data at the primary hash. In terms of file systems, our distributed hash table effectively is kind of like a flat storage bucket, so you can kind of think of it as functioning very similar to AWS S3. And so applications that you build on top of this would be pretty similar. Obviously, some of the performance characteristics would be a little bit different, considering this is peer-to-peer and not located in like a centralized AWS data center. Fault tolerance, or nodes are able to detect and recover from node failures and restore the overlay network. And that's basically possible because we have backup data. So like if a node can't access its neighbor, it's able to then jump to the neighbor's neighbor and then update that next relationship. And creativity, we use that Fibonacci sequence to make our finger tables more efficient. And we have a pretty neat chord crawler algorithm that does cycle detection and detects if our overlay network splits into two, things like that. Haven't had any issues with that in particular in a while, but it's pretty neat that we have that. Yeah, so that's everything. If you are interested, feel free to clone our GitHub repo. So here's the repo. And we have pretty good instructions on how to basically go through everything I just showed you. If you have any issues, feel free to file those, and we'll get back to you. Like I mentioned, if you want to implement a peer-to-peer application on top of our code, you're basically not going to want to touch our Chord node logic here. You're going to want to extend and then do all the customization and the child class. And so follow this user service class as an example there. So thank you very much. I hope you all have a wonderful day. Bye.